Zwitter ion, yes.
Yeah,
It's the Pi is the isoelectric point. Okay, this Pi stands for isoelectric point. Okay, it's the pH where the Zwitter ion is most dominant. So that is our definition of Pi. It's called the isoelectric point. And what is the Zwitter ion again? What charge would the Zwitter ion be?
Zero.
This will be neutral charge or zero charge, right? So the whole molecule will be a charge of zero, or the whole molecule will be a charge of neutral. Okay. So we did one for alanine. I don't know if you remember that from last week. We did the isoelectric point for alanine. Let's do one more amino acid. Okay. This amino acid that we will calculate the Zwitter ion of is called histidine. Okay. Histidine. Okay, what's the one-letter amino acid abbreviation for histidine? Okay, that happens to be pretty easy, H. Okay. Okay, three-letter amino acid abbreviation is HIS. All right, so the first thing we'll do if you're asked to calculate the isoelectric point or the Pi of a substance is, first of all, we'll draw it. So if you have your flashcards, you should draw them totally protonated. Okay, totally protonated. So what is the structure of histidine? Okay. We have an NH3, okay, totally protonated there. And when that nitrogen is totally protonated, it has a positive formal charge. So we call that an amine, okay, the amine group. We have an alpha carbon for this amino acid histidine. We have an alpha hydrogen. We have an alpha carboxylic acid group. And then we have a side chain. So the side chain for histidine is called imidazole. Have you heard this functional group before? You may not in organic. It's called imidazole, the imidazole functional group. So I will draw the structure of the imidazole functional group. Let's see, how should I draw it here? Anyways, I don't think it should be. Okay. CH2. Okay, so on the test or on the exam, you can use your flashcards. But the imidazole functional group is right here. I have a C double bond with the CH. It has this complicated ring structure. Okay, we have a nitrogen here. Okay, that's bound to an H. We have a carbon here. That's bound to an H. And we have a nitrogen here. That's bound to an H. And we have a double, okay, so that CN is a double bond. Okay, I'm just using my flashcards just like you guys are. Okay. And that nitrogen forms a bond with that carbon. So this nitrogen here with the double bond to this C, with this single bond to that C, and bound to a hydrogen, this has a positive formal charge. Okay, so I just drew that from my flashcards. A lot of these I've memorized, but unfortunately I have not memorized histidine, so I'm sorry. All right, so we draw the structure of histidine in calculating the Pi of histidine. Okay, we will calculate the Pi of histidine. The isoelectric point of histidine. So this has 3 pKa's. Okay, can someone tell me one of the pKa's? What's the pKa of the alpha amino group in histidine? 9.33. Okay, we'll go with that. What is the next pKa that you guys found? They vary from books to books, and I'm finding that there's a lot of variation. I think a student told me that I think it was you, Jasmine. What about carboxylic acid? 1.80, okay. Okay, so this, one of these protons, okay, so use your flashcards, has a pK of 9.33. One of these protons has a pKa of 1.80. Anything else you see here? The side chain. And what was that? What is that? 6.04. Okay, 6.04. Sounds right. Okay, so here we have histidine. In your flashcards, make sure it's totally protonated. Everything is protonated. Everything is protonated as it should be. And I'm going to call this the 1.80. I'm going to call that pKa1. I'm going to call the 6.04 pKa2, and I'm going to call this alpha amino group at 9.33 pKa3. Okay, let's call it pKa3. All right, how do we calculate this pi then? Okay, so we have it totally protonated. Okay, a very acidic pH. And then we raise the pH, we raise the pH, we raise the pH until we get to a pH of what? 1.80. Okay. Now before I move on, what's the total charge of this whole molecule? +2. So this is the whole histidine molecule has a +2 charge. Now, and we'll call this form 1. Okay? Lack of a better term, form 1. So now we're at pH 1.80, and then this alpha carboxylic acid proton begins to come off at pH 1.80, which is the pKa of that carboxylic acid, alpha carboxylic acid. So this is now what we will start to see here. I'll draw that side chain. So I'm going to call this form 2. Okay. Okay, I'm going to call this form 2. And what's the charge of form 2? +1. Okay. So we have two forms of histidine now once we get to 1.80. At pH 1.80, how much of form 1 and how much of form 2 do we have? 50-50. 50-50. All right, now we're past 1.80. At pH, 3, how much do we have more of? pH 3 will have more form 2, correct? So the proportion shifts, okay? We'll get a little bit of this, but a lot of that as we go further away from 1.80. Okay, we're going to continue on and on and on until we get to this magical pH of what's next? We got 1.80. Okay, we'll go to a pH of 6.04, and then what begins to come off? The hydrogen, the proton, the hydrogen from the side chain. The side chain for histidine, I'll write it out, is called imidazole. Okay, the imidazole side chain. I don't know if this is just trivia, but the imidazole is very good at chelating nickel, chelating metals. So if you have nickel in the cell, this histidine can, chelate it, meaning like sop it up. So this imidazole is very good at binding metals. Okay, the side chain of histidine. All right, so let's focus back here. So at page 6.04, this comes off. So let's draw the structure. This has come off, okay? This has come off, and as it comes off, it's going to leave a lone pair. That's just how nitrogen is. Okay? So here the proton has come off. Okay, here the proton has come off. And what's the total charge here? I'm going to call this form 3. Okay, this is form 3, and what's the total charge? 0. What do we call something that's a 0 charge? Okay, so this is called the Zwitter ion. I'll write it like this. So that form 3 is special because that form 3 is called the Zwitter ion. As you guys correctly stated, it's the pH. I'm sorry, not the pH. It's the charge. The whole charge is 0. Okay? The whole charge is 0. All right, I think we have one more left. By the way, at page 6.04, how much do we have? That is correct. Okay? We have 50% of form 2 and 50% of form 3. As we move away from 6.04, let's say pH 7 or pH 8, what do we have more of? Form 3, and this begins to slowly, get deprotonated at the side chain as we go farther and farther and farther away from pH 6.04. And I believe we have one more to go. Okay, we'll put that here. And then we will reach a pH of 9.33. Okay, and what begins to come off at pH 9.33? One of the protons will come off. Which one is that? The primary amino group. That proton comes off. So let's draw the structure now. Bless you. Okay, remember this has come off. Bless you. By the way, just for consistency, there is a lone pair here, okay, on the nitrogen. Okay, I'm going to call this form 4, but what is the total charge on form 4? What's the total charge? This is -1. Okay. All right, so how many forms of histidine can there exist in theory? 4. Okay, there can exist 4 forms of histidine. Okay, in the cell. And it's all dependent on the pH. Okay, so to calculate the isoelectric point, which is the pH where the Zwitter ion is most dominant, what can we do here? So this is the Zwitter ion. At pH 6.04, we have 50% of the Zwitter ion, which is what we care about, and 50% of that, which we don't care. So 6.04. And then at pH 9.33, we have 50% of the Zwitter ion, which is what we care about. And then this, which we don't care about, so plus 9.33. The place, or the pH, where this is the highest, most populated, would be the average. So 6.04 plus 9.33 divided by 2. What is that on our calculator? .04 plus 9.33. We'll divide that by 2. 7.68. We'll call it 7.7. Okay. So this is the PI. So at pH 7.7, histidine has the Zwitter ion most dominating. Yes, sir.
Why did you not add 1.80 to the PI?
Because this has nothing to do with the Zwitter ion, Mustafa. The Zwitter ion is where this is most dominating. And it's most dominating 50% here, and it's most dominating 50% at this pH. So form 1 has nothing to do. In other words, if you want to calculate the PI, where the Zwitter ion is most dominant, you're going to take the flanking things that are surrounding the Zwitter ion and average their pHs. That will be the pH where this is most dominating. This has nothing to do with the Zwitter ion. Once again, at 6.04, it's 50% this and 50% that. At pH 9.33, it's 50% this and 50% that. At pH 9.33, it's 50% this. At pH 6.04, it's 50% that. We're interested in the Zwitter ion. At pH 1.80, we barely even have, we have 0 of this. We have nothing of this, okay, at the Zwitter ion. So 7.70 is what we calculate is our isoelectric point. So anybody remember, there's some leeway here, anybody remember what is physiologic pH? What is a pH inside our cell, typical cell? Okay, 7.2, 7.3. We'll go with 7.2, but you can say 7.3. I've also heard 7.4, by the way, so. Physiologic pH. I heard cell physiology here, so Dr. G would know. I'll ask him after class. So physiologic pH will go with 7.2, but 7.3, 7.4 is just as good. Okay. So what do you notice here? Okay, this PI closely matches what? The pH inside our cell. Okay, what's the best buffering capacity? The best buffering capacity, right, pKa plus or minus 1, okay? pKa plus or minus 1 is the best buffering capacity, okay? So the question I have for you is, what is a good buffer inside our cell? Natural buffer. So where pKa is, so the best buffering capacity inside our cell would be, I don't know, 6.2, 8.2, okay? Because this, I think I'm not saying this right, but because this has a pH 7.7, what is the highest form? The Zwitter ion. What is the pH inside of our cell? 7.2. So what's the best buffer inside our cell? The best buffer inside our cell is histidine. Okay, this is a natural buffer. Okay, so if your pH gets acidic, okay, the protons will be there. If the pH gets basic, it will take away the protons. Okay? So the best buffering capacity inside our cell is histidine. Okay? Because its Zuider ion is close to the physiologic pH. So if it gets really basic, it can be the -1 charge. If it gets really acidic, it can take on the +1 charge. So it can withstand, histidine can withstand some, fluctuations in pH. Because if your cell environment gets too acidic, it will shift to form 2. Okay? Let's say if you're below physiologic pH. If you're above physiologic pH, it will shift to form 4. Okay? So this is the best buffer inside the cell. Histidine is a natural buffer, is the take-home point. Okay, everybody understand this? Okay. What's the best buffer? Histidine. Okay. Histidine has the best buffering capacity because its Zuider ion so closely matches the physiologic pH. So if your pH goes too high, that's okay. You'll get more of form 4. If the pH is too low, that's okay. You can get more of form 2. So it can withstand that pH. It can take protons or it can accept protons. Does everyone understand this? Yes? It can take protons, accept protons. This one here. So the best buffering capacity is where pH is equal to pKa plus or minus 1. Histidine can be histidine can be a good buffer at around 6.7 to around 8.7. Okay? 6.7 to 8.7. Is this kind of clear? If it's not clear, just know histidine is a good buffer. All right, but do you know why it's a good buffer? Okay, its Zuider ion is so close to the natural pH inside our cells. Okay? So that if it gets too acidic, it will take the proton. If it gets too basic, it can give away the proton. Okay, its best buffering is 6.7 to 8.8. So if your cell pH gets down to 6.7, no problem, histidine is there to get it close to physiologic. If your cell, for some strange reason, gets too basic, okay, if it gets too alkaline, that's no problem. Histidine will be there to get it back to 7.7 or close to physiologic pH. All right, so that is what I wanted to mention to you guys about that. All right, any questions or comments before I go back to the PowerPoint?